Hi, this is an addendum to my video called Anagraphs, and what I want to do is walk through some proofs of two interesting, I think, facts about the anagraph problem and the Kerning problem, actually generalized versions of these problems. And if you didn't watch the other video, you should just watch that one first, or maybe only. This video is substantially less polished. It's basically a lecture about a thing that I think is interesting and you might find interesting too. It doesn't contain any jokes or anything like that. It's just some computer science. And the thing I want to talk about is, can these problems be solved at all? It may surprise you that a problem can't be solved and that we could know that. In particular, I'm going to be talking about whether a computer could solve, say, the Kerning problem in general. The answer to that happens to be no. And I'm going to do that using this technique called reduction. We're going to talk a bit about Turing machines. And if you feel like you already know this stuff, but you decide to watch anyway, I encourage you to try to anticipate where I'm going, and in particular, try to spot mistakes that I'm making. Because there are some mistakes that are sort of deliberate, because I'm capturing the process that I went through as I wrote this proof. Of course, I correct those mistakes and point them out. It's part of the point. And another part of the point is I want to give a bit of a sense of what constitutes a proof. Because things that superficially look like proofs sometimes have serious mistakes in them. And that's something that I think is pretty important to be sensitive about. So, welcome to Tom Academy. In the other video, I introduced the anagraph problem and the related Kerning problem. These are very similar, but one turns out to be possible and the other is actually impossible. And I'm going to use a similar technique to prove both of those results called reduction, and this is a very powerful technique in algorithms. So what I'm going to do in this episode is describe those two problems precisely, then wield that reduction technique in two opposite ways to prove that this one problem is possible and the other is not. Okay, so these both come out of this idea of anagraphing, which is like anagrams, but where I can break apart the letters. In the other video, I was pretty loose about this, but it's important to be precise if we're going to prove something. I also want to emphasize that these problems are both easy for English letters, so we're really talking about the generalized problem here. So here's a precise statement of these two problems. You have a set of letters, and I could use English letters, but I could also have some Japan, I don't know what that is, pi, and I could have some other weird alien letters in there, something like that, right? So just some large or small set of letters. Also, since we break apart letters, I need to include these partial letters, like we might say that the A breaks into these two things. And I previously called these atoms and distinguished them from letters, but in the generalized problem, there's just going to be some set of symbols, which we'll just call letters. They're all the same. Our word will just be a sequence of these letters, any of them, so I could use that little I thing without a dot a few times, and then maybe one of these, and then a B. Okay, that's a word. And since this is a generalized problem, I don't care about these being English words. And finally, I have some rules, and this is the essence of the problem. The rules let me break apart and combine letter sequences to make other letter sequences. So, for example, I said that the B could become, all right, like this, L followed by, oops, I didn't draw that too well, L followed by O. And it's not just about breaking down a letter, but I might say that, for example, AA, I'll draw you what this might look like. AA is kind of like if I join them together, then I might pull these parts off, and then I might rotate these around so I get TVT, right? So I might have a rule that says that AA can become TVT. Now these rules operate in either direction, so I can turn LO into B and B into LO. And another thing to note is that there can be more than one way to rewrite a particular sequence. So we saw in the previous video that D, you could have a rule that makes D turn into OL, but also it would make sense to have a rule that turns D into CL. And in fact, we saw a way that I could combine this with a rule like O rewrites into CC, the two halves of the O, to create an infinite number of C's. So this can get kind of complicated. For the generalized problem, just like I don't care about these being real letters or real words, I don't care about these rules being sort of physically realistic. So while this is a fine rule, I could also just have one like cat rewrites to dog. All right, now, so the generalized anagraph problem, let me clean up here. So the generalized anagraph problem is, given an alphabet and rules as we discussed, and the ability to rearrange letters at will, and given two words, W1 and W2, can I turn W1 into W2? That's the anagraph problem. This problem is solvable, but in my opinion, it's not obvious. So what I want to talk about first is the Kerning problem, which turns out to be unsolvable, and that might give some intuition about why this one is harder, or might be harder than you would think. In the Kerning problem, I simply lose the ability to rearrange letters. And so I call this the Kerning problem because, for example, I can take, if I have a rule that says Rn becomes M, I can make Kerning into Kemming, but not, for example, Kenimg, because I can't move this R over here in order to combine it with that N, only the one that it's already next to. It might actually be more appropriate to call this the ligature problem, because ligatures in typography allow me to rewrite some sequence like FFI into some fancy character like this, where the F's are collaborating and the dot on the I doesn't interfere with the top of the F. But for some reason, kerning has a certain mystique to it that appeals to people. So I'm just going to call this kerning. It obviously doesn't matter. But the question is the same. Given two words, can I turn W1 into W2? So I'm actually going to prove something about a slightly different problem, which is, can I turn W1 into some W3? And I get to pick W3, where W2 appears somewhere inside W3. So for example, instead of asking, can I turn kerning into Kemming, I ask, can I turn kerning into some word where Kemming appears inside that word? It's not really that different, and I think it helps capture the basic ideas here, but it will help me actually make this proof go through. So I want to show that this problem is not possible. What do I even mean by that? Well, first of all, to say we can solve the problem, we have to be able to solve it for all instances, not just that one example that we just saw, and not just easy ones. In fact, we have to solve it for really devious inputs, so it's useful to think of the inputs as coming from some clever adversary. Skeletor gives us an alphabet and gives us the rewrite rules and a pair of really tricky words. And then to say that we could solve the problem means that we have a procedure that works no matter what Skeletor gives us. It's not just enough to believe or assert that we'd be able to do it using our cleverness applied to each instance. We have to come up with some procedure. And so what we're going to do is actually prove there is no such universal procedure. Now, incredibly, in computer science, we figured out that any procedure can be performed by a simple computer called a Turing machine. This thing is kind of unbelievably simple. You have an arbitrarily long tape, which just has ones and zeros on it. We think of the end of the tape as just having zeros off forever in both sides. This is kind of like how you could imagine as many leading zeros on a number as you want, and it means the same thing. The Turing machine also has a cursor, which I'll draw like this, which points at one position on the tape, like the read-write head of your VCR. And then the cursor always has some state, which we'll give as a letter. Here, I'll just call it A. And finally, there's a table of rules. And the rules tell the Turing machine what to do in each of the situations it might be in. So since the cursor always has a state, we have to list all of the states here. And because the cursor might be pointing at a 1 or a 0, for each state, we have to list both cases, 0 and 1. And then we say what happens in that situation. And what happens is we change the symbol. For example, I could say that if I see a 1, it becomes a 0. And if I see a 0, it becomes a 1. Then I have to say what new state I'll be in. For example, I might be in state B here, but I might stay in state A here. And then I must move the cursor either to the right or to the left. Since I talked about this state B, I need to say what the rules are for state B. And that's the whole thing. The table just has some set of states and the rules for what to do in those states. And what the machine does is just look up what action it should take. For example, here, I'm in state A and I'm pointing at a 1. So I write a 0 in that spot, and it says I'm supposed to move to the right. So now I'm pointing at this one, and I will end up in state B. Now in state B, I'm looking at a 1, so I write a 0. My new state will be B, and I move again to the right. And if you're learning about this stuff or you're pedantic, I'll note that there are many different ways to describe Turing machines that turn out to be equivalent. So this is just one particularly simple one that I like. Speaking of simple, it's really mind-blowing to me that something so simple could allow us to build any procedure. If it can be done by a Pentium, it can be done by a Turing machine. If it can be done by a quantum computer, it can be done by a Turing machine. We've never discovered, and we don't expect to discover, any physical procedure that allows us to solve more problems than a Turing machine can. And that's pretty cool and pretty useful. Actually, there are even a lot of alternatives to Turing machines that are even simpler to describe, and Turing machines aren't even my favorite one. For example, I think the lambda calculus is more beautiful, and the combinator calculus is even simpler. But this one is traditional, and it's very useful for this particular problem. You may in fact already see some parallels between this tape and the word in the Kerning problem. So what we could do is prove that there's no Turing machine, really a Turing machine program, like a table like this, that solves this problem, the Kerning problem in general. It's usually really hard to prove that something doesn't exist, although it sometimes can be done. In this case, there's already a powerful and ancient non-existence proof for Turing machines. I'll call this the Turing machine oracle problem because I'm going to give it a prediction of what I think the Turing machine might do. That's the final tape. And ask, is that right? So the statement of the problem is this. I'm given a Turing machine, which is described by these rules, and an initial tape, which includes the cursor's position and its state. And I'm also given a proposed final tape, which has also the cursor and state. And then the question that I'm being asked is, does running the machine, starting at that initial state and following the rules, ever produce the proposed final tape? And with a Turing machine, each step just looks at this tape state and transforms it to some next state, T1, T2, T3, T4, ... And there's no ambiguity about what I do. I just look up the rule and apply it. So the question is really, does this sequence contain that proposed final tape, TF? And amazingly, impossible. The oracle problem is undecidable. I'm not going to explain how that proof works in this video, and there are hundreds of good descriptions of it out there. You could search for the halting problem. It's not the same as the oracle problem I just described, but the argument is roughly the same. It's called the halting problem because this sequence T1, T2, T3 might go on forever without ever returning to a state that I've seen before. And if that's true, then I don't know if I will ever get to the target state, TF. But it's not exactly the same as the problem I just described. Same idea, though. This proof is utterly beautiful. It's maybe my favorite proof of all time. The basic idea is that we assume that there's some oracle, and then we use the fact that that oracle must be given as a Turing machine, since it's a procedure. And then we make our own Turing machine that runs the oracle Turing machine, simulates it, using our own machine, which is also a Turing machine, as input, and then gets the answer. What will the oracle say if asked about me? And then it can perturb that answer. It can switch it, say yes when it would have said no, and so forth, thus ensuring that the oracle always gives the wrong answer when fed T. I know I went over that too fast, but it's a really good problem if you like this kind of thing. So anyway, it's well known that there is no such procedure for solving the halting problem or the oracle problem. The oracle problem, again, is does the Turing machine ever get to a specific tape state? Oh, look, I misspelled oracle. So I'm going to use the fact that there's no solution to the oracle problem in order to prove that there's no solution to the Kerning problem. The argument's going to look like this. First, you give me a Turing machine oracle problem. That means you give me the rules and those two tapes. I'll turn it into an equivalent Kerning problem. This step here we're actually going to do. This is the reduction part of the reduction argument. Next, imagine that we could solve any Kerning problem. This is an assumption that we make for the sake of contradiction. This will turn out to not be true, but we're going to imagine that that's the case. And then we see that we have the contradiction. This is impossible because if I could solve any Kerning problem, then I could solve any Turing machine oracle problem, because what I do is I turn the Turing machine oracle problem into a Kerning problem, solve that, and then I have your answer. Since we know that can't be done, we know that there's a problem with one of our assumptions, and this is the only one, this hypothesis that we could solve any Kerning problem. So we know that that can't be done. So this is both a proof by contradiction and a reduction proof. Later on, we'll use reduction to prove the opposite kind of statement, that a problem can be solved. So all that's left is to show that this step can be done, that I can turn any Turing machine oracle problem into an equivalent Kerning problem. And that's what the rest of this is about. So we get a Turing machine, which is some rules, that table of rules, and we get an initial tape, T1, and a proposed tape, TF. And we're going to produce an alphabet, rules, and words, W1 and W2. That's how the Kerning problem is parameterized. And this will involve coming up with a fairly devious alphabet and set of rules. So we'll be playing the role of Skeletor in this case. But we're allowed to do that. Supposedly someone has come up with a solution to the general Kerning problem, and that would enable us to solve this other actually impossible problem. So I'm going to refer to these things that we make as Kerning machines. So the first step is, let's talk about how we turn T1 into W1. T1 is some tape, like 1, 0, 0, 1, 0, 1, 1, 1. In the Kerning machine, we will actually just represent that as the word 1, 0, 0, 1, 0, 1, 1, 1. Same thing. Now the Turing machine also, the tape has a cursor, and the cursor indicates a particular symbol, in this case that 0, and has a particular state A. So what we're going to do is actually alter the representation of this word. So what we're going to do is introduce some new letters, bracket, left bracket, and right bracket, and then the symbol A, which will correspond to that state. So our letters so far in the alphabet are 1, 0, left bracket, right bracket, and A, and any other states that the Turing machine has. So B, C, D, dot, dot, dot. So the cursor is represented by these brackets surrounding the symbol in question. Okay, maybe you even see where I'm going with this. It's not really that complicated yet. So now let's go back to that table of rules, which is the other thing that comes with our Turing machine. This table could have as many states as it wants. I'm just going to do this example where there's these two states. Now for each rule in this table, we're going to produce a rule in the Kerning machine that implements it, or simulates it. So let's look at that first one. The state is A, and the tape is 0. This actually corresponds to the situation we see right here. Brackets surrounding a 0 with the state of A. Now how do we say that what we want to do is write a 1, become the new state B, and go right? So this is going to correspond to a kerning rule, and so I need to figure out what goes on the right here. Okay, so a little trick. Let's first pretend that we had the ability to say any character that appears here, any letter that appears here. Then what I would do is I would say, well, I want to move the cursor right. So now it is surrounding whatever was there, that star. And then the new state, reading the table, is B. And since we wrote a 1, that 0 that used to be there is now a 1. Okay, this actually works fine. When I recognize that pattern, I'll move it to the right and put a B. So if I were to execute that on this string up here, I'd get 1, 0, 1, bracket. There's a 1 here that fills in for the star, and then a B, and then a 0, 1, 1, 1. Okay, that would be the result of applying this rule, and in fact, it's what happens to the Turing machine. Let's actually look at that. I think it might be useful to see the example. So this would write to 1, 0, 1, 1, 0, 1, 1, 1. And now the cursor is pointing at this 1 and a B. Does that make sense? And so we could actually say that that used the rule A0, because the state was A and I saw a 0. So let's actually annotate that here. Now this pink asterisk here is made up, and I can't do that. I don't allow for wildcards in the Kerning problem, but there's only two things that could appear there, a 1 and a 0. So what we can do is we can just take this rule and make a second copy of it. I'll just make two versions, one for the case where there was a 0, and one for the case where there was a 1. And then I can preserve that symbol. So each rule in the Turing machine's table will become two rules over here. And in this particular case, because the symbol to the right is a 1, I would have used, in fact, this version of the rule. Okay, let's do the next row just as an example. Here I'm going to move left, so it'll be a little bit different. Okay, that's this one and that's this one. Here the brackets will contain 1 because that's what I'm seeing, and I'm marking that I'm in state A. But I'm going to move left, and so I need to match a letter to the left. I have to do the 0 case and the 1 case. So that rewrites to brackets around the 0. The state is A. I'm just reading that off the table. I wrote a 0, so that previously bracketed thing becomes 0, and that's it, nothing to the right. Like above, I need to cover both cases, so a 1 followed by 1 in brackets. Either way, I'm in state A, and I write a 0. But the thing in the cursor is whatever I matched to the left. So this would be the case where I had that pink asterisk sort of on the left of the brackets to match 0 or 1. Okay, makes sense? So you could probably guess where I'm going with this. I can turn T1, a tape, into one of these words. I can create these rules, and then I can turn TF into word W2. Then I can ask the Kerning machine, can you turn W1 into W2 using these rules? And if I can, then I can do it in the Turing machine and so on, right? Well, there are a couple of problems. And if you feel good at this kind of stuff, feel free to pause right now and try to debug my work, because I think there are at least two serious issues with this. Okay, we'll start with a superficial one. And that's that in a Turing machine, in order to make room in the tape to do sort of arbitrary amounts of work, I pretend, or rather I say, that there's infinite zeros on either side of the tape, already sitting there forever. But in the Kerning machine, the word is just all right there. I can't just put an infinite number of zeros on either end of the word. And in fact, all of these rules preserve the length of the word. So that's a problem. So how am I going to fix that? This turns out to not be very hard, actually. So what I'm going to do is I'm actually going to say, I'm going to add 2 new letters to my alphabet. Curly brace left and curly brace right. Let me make those not look like 3s. I don't have to be that sloppy. In Tom Academy. Okay, and what I'm going to do is that the encoding of any tape is going to have these curly braces on either side of it, always, and I'm just going to maintain that as an invariant. And then each one of these rules has the possibility of applying when the cursor is at the very end or very beginning of the word and tries to move out of it. And then what we'll do is we'll just pretend that there's a 0 there. So in the case of this first set of rules, let's work on that first. Since I'm moving right, I have to think about the case that the cursor is at the end of the word, that is, next to this curly brace. So I'll add a case for when I'm looking at 0 in state A, but instead of a 0 here, a curly brace. And then I'll just simply allow to extend the word. This is going to be an exact copy of this other 0 case. 1, cursor is now looking at a fresh new 0. It's in state B, and I have to preserve that the end of the word marker is right there. Okay? And then in the moving left case, it'll be the same idea, except on the left. So instead of seeing a 0, we'll see the end of the word on the left. And I'll be looking at the end of the word marker, and then the cursor will be on a new 0, state A, and I'll have written a 0 behind me, just like in this rule. So that's a pretty easy fix. And because these symbols don't appear in any of the other rules, they won't interfere with anything. And so basically every one of these Turing machine rules turns into 3 rules instead of 2 in the Kerning machine. Okay, so now we're done, right? T1, we wrap it with these curly braces and transform the cursor. And then TF, we do the same, and then we ask, can I turn this word into the other word using those extended rules? Okay, but this has a harder problem. It has to do with the fact that these rewrites in the Kerning machine are bidirectional. They allow me to go forward and backward. So if you want to test yourself, see if you can figure out why that's bad and what you would do about it. So here's what goes wrong. The Turing machine can only do one thing at every step. It takes tape 1, which produces tape 2, following whatever rules in the table, and then that makes tape 3, and so on. Now, in fact, the way we set up the rules in the Kerning machine, the Kerning machine, it can do what the Turing machine does. So W1 could become W2, which could become W3, and each of those corresponds to the Turing machine using the way we described of turning the cursor into brackets and putting curly braces around the outside. But the issue here is that I can run these rules in reverse as well. So W2 could become W1. So what I could actually do is say W1 goes to W2, goes to W3, but then back to W2, and then I could go to W3 again, and whatever. This isn't really much of a problem because if I go back from W3 to W2, I didn't really do anything that the Turing machine can't do. I just wasted time revisiting a state that I was already in. But there is an actually serious problem here, which is that if I run rules backwards, I might get into a place that I couldn't have gotten into otherwise. So let's think about a very specific Turing machine. This is the tape wiping Turing machine. And in this machine, it just has one state, A. And what it does is it always writes a 0, no matter what it sees on the tape, and then stays in state A and moves to the right. So it's pretty easy to see that for any tape that I might give this, I put the cursor at the very beginning and I say A. Well, it's going to see a 1 or a 0 and it's going to write a 0, and then it's going to go to the right and it's going to see a 1 or 0 and write a 0. So no matter what, all this Turing machine does is fill the tape with zeros. 0, 0, 0, 0, 0, 0, 0, and then the cursor stays in state A and it keeps moving to the right. Now I think this is subtle and interesting. In the transformation that we gave, we would get 6 rules. I'm going to ignore the ones that happen at the boundaries because they're actually not relevant to this particular problem. So these rules basically say the cursor is surrounding some number, be it 0 or 1, and there's some bit to the right, and I move my cursor to the right and I write a 0. So it's faithful to these. The problem is that there are multiple rules, that there are multiple things on the right-hand side here, like these two, that are actually the same, and these two, which are actually the same. So let's say that we started with this tape. We know that this Turing machine just writes zeros everywhere. So if I run these things only to the right, I'm going to get 0, 0, 0, 0, 0, and then this last one will be bracketed with the state. It will be A. That's faithful. We've cleared the tape. So I ran that all the way forward, and I got into this state. But now I can run rules backwards, and I don't have to run the rules that I ran to get here. In particular, if you look at this one, this part here matches this, right? So I can run that backwards, and I get 0, 0, 0, 0, 1, A, 1. And that matches this again, so I could do that again. And if I want, I could fill this whole tape up with ones. And that was not something that this Turing machine could ever do. All this Turing machine does is wipe the tape to all zeros. But since it works on any tape, any sequence of bits, if I run that backwards, I can unwipe a tape that consists of all zeros into any other string. So the upshot of that is if I were to ask, hey, can I turn the tape 11010, 11010 into the tape 10101, ignoring the cursor position at least, the Kerning machine would say yes, because I could wipe that all to zeros and then unwipe it to any sequence that I want. And this is totally wrong. The ability to unwind to rules that I didn't actually run ruins this correspondence between the Turing machine and the Kerning machine. So how do we fix that? This turns out to be trickier than just adding curly braces on the ends. So the way I want to fix this is ensure that the Kerning machine only takes forwards and backwards steps that the Turing machine could actually take. So the output of the Kerning machine, although it might go back from W3 to W2, that will always correspond to going back from T3 to T2. And we believe that that's safe because we can just get rid of these excursions. I know I'm being a little fast and loose with that, but I believe that that's true and that we could prove it. What I won't let us do is go back to a state W5, or WX, I guess, that doesn't appear anywhere in this sequence, like we did when we unwiped the tape in that last example. The way I'm going to do this is to record a trace of the exact Turing machine rules that I applied at every step. So instead of the word just being a curly brace with some bits, 10010, a cursor, a state, and then some more bits, I'm going to make some much better curly braces. Oops. Have pride in your work. What I'm going to do is I'm going to record a trace outside of the string here. Now the sequence of rules that I apply in order to transform one word into another could be arbitrarily long, but I have arbitrary amount of space out here. And the fact that I use this curly brace will actually turn out to be very handy. So I'm going to add some new symbols to my alphabet, which was square brackets 0, 1, A through Z for any states that I might have. I'm going to add a less than and a greater than and a bar. And I'm going to add 2 new letters for each state, A with a ring on top like the angstrom, and A with a tick on top. Those will stand for A0 and A1. These are the names of the rules that came from the table, A0, A1, right? And I'm doing that so that every rule has a unique symbol and that I don't get those symbols confused with anything else like the names of states. Then I'm going to modify these rules. And what I want to accomplish is that whenever I apply a rule, I want to put the name of the rule that I used, which might be A0 or A1, as this symbol A0 or A1, like that. I'm going to put that on the end of the trace. Okay. This turns out to not be too hard in a Turing machine. It's kind of cute, actually. So let's just look at one of these rules as an example. I'm not going to try to write everything out here because it gets pretty annoying. Let me first actually label all of these so that we don't lose them. This pair of rules is A0, and this pair of rules is A1. Okay. Now looking at A1, which actually has these 2 parts, I'm looking at the bottom one here. The way I'm going to change this is to say, after I apply the rule, instead of just immediately enabling the cursor here, I'm going to switch into a different state. Get rid of the left bracket and replace it with a bar. And make this less than sign, which I'll call the shuttle. And then I'm going to put the name of the rule that I used. I'm going to write this in pink so it's distinct. And that was rule A1. So I'm going to write that as the letter A with a 1 on top of it. Now after applying this rule, I'm in a state where I don't even have a cursor anymore. So none of the cursor rules are going to apply anymore. The only rules that will apply will be these shuttle rules, which I'm about to write. And the shuttle rules are going to bring that symbol all the way from here over to the trace and put it at the end, and then they're going to bring the shuttle back. So what do those rules look like? If I have a 0 followed by a shuttle, and then I'm going to use that asterisk meta notation again, some rule name, then this thing becomes a shuttle followed by that rule name followed by a 0. So in this particular example, that would rewrite to, let me draw this pipe with a break in the middle because I don't want it to be confused for a 1. I just realized that that's a problem. Okay, now this rule will keep applying. Oh, of course we need one for 1 as well, right? Same idea. So it just moves the shuttle through all of the bits off until it gets to this curly brace. Then, quite simply, we'll deposit the rule name there. And I don't want the shuttle moving to the left now, so I'm going to use the greater than character to mean go to the right. And then I need these same kind of rules, except without this star, because that's already been deposited, in order to move the shuttle back to the cursor. So those look like this. A greater than followed by a 0 just becomes a 0 followed by a greater than, and same for 1. Finally, the shuttle is going to come back to the bar, and that's when we're going to re-enable the cursor. So that just looks like this. So let's say that we had this case, and the trace was already B0, A0, B1. And I just applied that rule that I wisely deleted from the screen. The rule came from A1, so I put that A1 symbol. The shuttle basically moves this thing all the way over here, replacing it with that, of course, one step at a time. Apply this rule over here, which puts this A1 on the end of the trace and turns around the shuttle. Then the shuttle swaps with each one of these things, giving us, first 1 shuttle 1 0, then 1 1 shuttle 0, and then 1 1 0 shuttle, right? So now the string looks like 1 1 0 shuttle, and then this rule allows me to restore the cursor, so that becomes a bracket. And of course this thing was always over here, and as a result we took the step, but we recorded which rule we used at the end of the trace. And as we do this, the trace will get longer and longer, reflecting which rules I actually took from the Turing machine. So to be a little bit more precise, we have to extend all of the rules to change their right-hand sides, to put that shuttle in there and the rule name. So these rules up here would have something like shuttle A0 bar, bar, and shuttle A0 bar, right? And so on. Then, of course, I don't have an actual star here, so I have to replicate these rules, one for each of the Turing machine rules, A0, A1, B0, B1, and so on. But that's no big deal. There's a finite number of those. Same with this. And what have I really accomplished with that? Well, all of the Turing machine rules can still be applied. And once I apply one, I have to do this shuttle dance to move it and put it on the trace and come back before I can apply another rule. As a result, if I apply a rule in reverse, which I still can do, I can, in fact, move the shuttle, I can in fact go from this state and turn this left brace into the shuttle again and the bar, move the shuttle back over here. I can then pick up this A and bring it back with me. And then I can run these rules in reverse. But because now this symbol A1 is there, I'm only able to run the rules from the A1 sequence, like these. Because only those will actually have the A1, which I didn't draw here, in the rule. I won't be able to match these other ones, which have A0. So although I can go back and forth with my Kerning machine rules, I'm always going to be following along a trace, or I'm going to be doing some of this shuttle movement within a trace. And in fact, there will only ever be exactly one rule that can apply in the forwards and backwards direction during the execution of this Kerning program. It might help the intuition to think about that wiping problem. Before, I was able to first wipe the tape to produce all zeros, and then unwipe the tape using any rules that I want to produce any tape that I wanted, right? What happens in this case is, as I wipe the tape, I record which rule I used in order to wipe the tape. But the numbers of the rules tell me what bits were there, because each rule matches a distinct bit. As a result, the trace actually contains, in reverse, the bits that I wiped from the tape. So when I try to unwipe the tape, I'm only able to unwipe it using the bits from the trace, so I get back exactly the tape that I had in the first place. So I think that's kind of pretty. Cool, but just one more thing to say here, which is that recall the Turing Machine oracle problem is, I have a T1 and a TF, and I ask, will executing the Turing Machine go from T1 via some sequence of steps to TF? And what I've done is created corresponding words so that I can ask the question, does W1 via some sequence of bidirectional steps get to WF? Where I showed you how to turn a tape into a corresponding word. But now my words look a little different. It's not simply a matter of putting curly braces on them, but I have this trace here as well. And this poses a problem, because if I take TF and I turn it into one of these words, I don't know what trace to put here. And so if my question that I ask of the Kerning Machine solver, this hypothetical solver, is, can you turn W1 into WF? I won't know what trace to say, and therefore I won't be able to ask the question. And it's not like I can do something like try all of the possible traces, because there are infinitely many. So this is why at the beginning of the video, I told you that we're actually going to prove a slightly different problem, undecidable. And that's the problem where I give you a W1 and I give you a WF, and I ask, is there some way to rewrite W1 to something such that WF is a substring of some word? And I need that because there's going to be this extra trace there at the end. I couldn't think of any easy way to work around this problem. And though I believe that the exact problem is undecidable, this proof does not demonstrate that. Let me know if you have any ideas. Okay, so this completes the proof that generalized kerning is unsolvable or undecidable. Now I said air quotes proof because I think it's actually quite easy to make small mistakes when doing this kind of work, and that we should only accept very rigorous proofs as proofs. This proof was not very rigorous, and there were a couple of parts where it might have superficially looked like I had done it, but then there was some surprise, and perhaps maybe there are more surprises waiting. In fact, when I was in grad school, one of the things that we worked on were computer systems for developing and checking proofs. And this required giving a much more laborious, if you thought this was laborious, much more laborious argument where everything was perfectly well spelled out so that a computer could check it. Even those proofs aren't completely rock solid because there could be a bug in the program or in the metamathematics that underlies your proof system, but they're much better than this kind of proof or even a proof that you'd see in a paper. When we would take a paper proof and formalize it in these computer systems, we would often find out that there were bugs in that proof. Sometimes it was a superficial thing. Sometimes it was actually a pretty serious problem that we found some workaround for. And sometimes the theorem was not true, and so the proof could not be fixed. So I encourage you to think about this spectrum of rigor in proofs. Proofs are still the best technique we have in mathematics by far, but not all proofs are created equal. Okay, so that's the Kerning problem. It is not solvable. So to recap, I just proved that the generalized Kerning problem, where I can rewrite sequences of letters into other sequences, is undecidable. I proved that by demonstrating that if we could solve generalized kerning, we could solve the Turing Machine oracle problem. But since we know that that problem is impossible, we know that the generalized kerning problem must then be impossible. Showing that we could use one problem to solve another is the essence of reduction. So now let's look at the generalized anagraphing problem. This would let me form the word Kerning because I'm allowed to rearrange letters in addition to rewriting them here. This problem turns out to be solvable. We can prove this by reduction as well, but in reverse. Here we'll prove that if we could solve some other problem, then we could solve this one. We can use an off-the-shelf result to solve that other problem, proving that this one is solvable. That other problem is a kind of logic called linear logic. My thesis was actually about logic, so this is a subject that's dear to my heart, and I'm in severe danger of this turning into an all-day lecture. So I'm going to try to keep this to a sketch and just give the basic intuitions. We'll see how that goes. Now, there are actually many different logics, and in fact, there's many ways to present any given logic. You may be familiar with axiomatic presentations. I'm going to use a totally different one that we like in proof theory, which is to define an entailment relationship. That means we're only going to make statements of this form, where this symbol in the middle is just a separator that you could read as proves. And all of these A's are propositions. Proposition is a statement about the world like, it is raining, or a combination of propositions like, it is raining and I have an umbrella. Or perhaps, it is raining implies that I have an umbrella. The things on the left are my list of assumptions, and the thing on the right is what I prove. So one very simple rule in this presentation, which is called the initial sequent, says that if A is one of my assumptions, then I can prove A for that same A. And note that I could have some other assumptions here as well. Init is just the name of the rule, and I'll talk about this line in a second. But it basically means that I'm done with my proof. If I want to prove something like A and B, the rule looks like this. This symbol here means and each of these other letters stands for an arbitrary proposition. So I can use this same rule no matter what A is, as long as each instance of A is instantiated with the same proposition. Okay, so what this means is the line sort of separates my obligations from my conclusion. And here there's two obligations, each one of these arrows. On the bottom, I'm going to prove that A and B is true, and proving that from the assumption C, so on. And I do that by two obligations. One, prove A is true from the assumption C, and so on. And prove B is true from the assumption C, and so on. And that makes perfect sense. If I want to prove A and B, I need to prove A, and I need to prove B. So putting these two rules together, I could form a complete proof of the following simple fact. If I assume B and I assume A, then I can prove A and B. And I use this rule on the left here, first to create those two additional obligations. And then I can use the initial sequent in both cases. I have the assumption A, so I'm done. And I have the assumption B, so I'm done. And again, the initial sequent has no additional obligations. So every proof looks like this. It's read from the bottom up. And then we apply some rules to form further obligations. And those might have further obligations themselves. Sometimes there's one, sometimes there's many. And then finally at the top, we will always be using the initial sequent to kind of cap it off, because that's the only one that has no obligations. So that's the basic idea. Another thing to mention is that I'm allowed to rearrange my assumptions at will. So here, instead of saying B, comma A proves A, I could say A, comma B proves A. And this is actually more faithful to what I did over here, because note that A is the first thing, A, comma, dot, dot, dot. I just say that these are a set of assumptions, or really a multi-set, and that they can be arranged at will. And looking ahead a little bit, this is actually where the anagramming is going to come from, this rearrangement. I want to show you one more rule, which is implication. So if I want to prove A implies B, which I'll write as this, the way I prove such a thing, well, I'll have some assumptions, C dot dot dot, and I'll add A as an assumption, and my obligation is to prove B. Now don't stress out about the difference between this double arrow and the single arrow. I haven't really explained it well. It's not that important for today's lesson, but arrow is part of the language of propositions, so it can appear inside propositions. And this double arrow only appears at the top level, and it's the thing we're defining, how to prove things. So each one of these propositional operators, like arrow or and, has a rule that tells us how to prove it when it's on the right-hand side of a proof. And there's also a rule for how we use that thing as an assumption. So I'll show you an example of that within an example of a proof that uses this. Here I want to prove the statement that A and B implies A. The way I do that is use that rule to move the assumption to the assumption side. So now I can assume A and B, and I'm trying to prove A. And then I use one of these left-hand side rules that tells me how to use an assumption of the form A and B. And that one's pretty simple. It just says that I get the assumption A, and separately, the assumption B. From there, I can apply the initial sequent and be done with my proof, because A appears on both sides. So what I just showed you was like regular logic, not linear logic. And I didn't even show you the whole thing. But it's enough to make the following point. What makes linear logic different is that I have to use all of my assumptions, and I have to use them exactly once. So contrasting with the rule above, where I had A, comma, dot, 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 proves A, in linear logic, I will just have A proves A as my initial sequent, and I won't be allowed to have anything else left over here. The rule for implication stays the same, although now we write this operator as what's called a lollipop or lolly. I'm not kidding. And this rule for and on the left stays the same, except now we write this thing as the tensor symbol for some reason. That just means and. But the rule for proving A and B has an important difference now. So if I'm trying to prove A tensor B, I'll still have two obligations, one to prove A and the other to prove B. But I have to take my assumptions C1 through Cn and I have to split them up into two parts, the first part and the second part. C1 through Ck, where k is some number between 1 and n, and then Ck plus 1 through n. So I don't duplicate the assumptions like I did up here. I actually have to decide which side they're going to be used on. Now, like before, I allow mixing these up any way I want. So this really just means I'm going to pick some subset of assumptions to prove A and some subset to prove B. Now, note how much this resembles the anagramming problem, where I have a bunch of letters, which are assumptions, and I'm trying to form some other word, which would be my conclusion, and I'm allowed to mix up those letters however I want, but I can't discard any or duplicate any. And that's basically where I'm going with this. So going back to this proof that I deleted part of unwisely, this proof no longer works in linear logic, even if I replace these with the correct symbols. Because although I can do this step, the step where I have the assumptions both A and B, and I try to conclude A, doesn't work because I still have this left over B. This is not allowed by the initial sequent in linear logic. I'll show you an example of something that I could prove, which will look a heck of a lot like an anagram. So here I prove that A tensor B implies B tensor A, and I do that by first applying the rule that I use when I'm proving implication, which takes this as an assumption. Then I use that assumption of A tensor B to get two assumptions A and separately B, and then I use the rule to prove B tensor A by having two obligations, and I split my assumptions A and separately B into those two different obligations and use the initial sequent from B get B, from A prove A. And note that AB is in fact an anagram of BA. So the fact that I use every assumption exactly once and I can't discard it or duplicate it makes it pretty easy for me to use linear logic to form anagramming problems. I'll take every letter in the input word and I'll tensor it together. I'll take every letter in the output word and I'll tensor it together. Then I'll ask, does that one proposition imply the other? And I'll do so with no assumptions. So that's cool, but where does anagraphing come in? That's where I have rules that can rewrite sequences of letters. Well, what I'll do is I'll just introduce those rules as other implications. Here I'm using capital letters, but we normally have that rule Rn can rewrite to M, so I can form that as a logical statement. R tensor n implies M. If you have both R and N, then you can form an M. And because I allow running these rules in both directions, I actually need the opposite as well, which appears to spell moron. But we're not morons, we're doing logic, and this is smart. So if I can fit this all on the screen, the way that I embed the question, does Kerning anagraph to Kerning with these rules, is to write it like that, but then also take as assumptions these two rules. And a proof of this will proceed by taking this thing as an assumption. I could have just written it on the left to begin with if I wanted to. Decomposing all of these letters into individual assumptions, then using these rules to rewrite those letters into other letters if I need to, and then proving this, which will involve splitting up those letters somehow so that I can assign them to the different obligations and finally use the initial sequent for each one. This almost works. There's one problem with it, which you may have noticed. Linear logic requires me to use every assumption exactly once, which includes these rules. Now, I will actually use this one exactly once in this proof, so that's okay, I guess. But I am allowed to use it multiple times in the full anagraphing problem. And then this backwards rule I won't use at all. And there's actually no way to fix that in this subset of linear logic. But this is a common problem in linear logic, and so we've invented or discovered another operator called ! Or bang. And the rules for how I use bang A are, if I have bang A as an assumption, then I'm allowed to actually take A as an additional assumption anytime I want, and I can do that as many times as I want. Additionally, if I have bang A as an assumption, I'm allowed to just throw that away and not use it. So that makes it pretty easy to fix this problem. I just take each of my rule assumptions, which I'm allowed to use as many times as I want, including no times, and I wrap it with this bang operator, which means exactly that in linear logic. Then I ask, can I turn this one word into the other? And that's it. I just showed how I could turn an instance of the anagraphing problem, any one, into a problem of provability in linear logic. Specifically, I only used these operators, tensor, lolly, and bang. This particular set of operators is called multiplicative exponential linear logic. And when I was in grad school, nobody knew whether it was solvable or not. Solvable here means, can I decide whether an arbitrary statement, A proves B, can be proved or not? But just a couple years ago, some wizards proved that it is in fact decidable. This is pretty cool, and I think it was a pretty elaborate proof, because in contrast, if you add just a few other connectives like A or B, then this is known to be an undecidable logic. You can code up Turing machines or something like that in it. So we've proved that the generalized anagraphing problem is solvable, because any anagraphing problem like this one can be turned into a MEL problem like this one, and MEL is decidable. then we've given a procedure for deciding any generalized anagraphing problem. This is a reduction like our previous argument, but in the opposite direction. We turned an anagraph problem into a MEL problem instead of turning a Turing Machine problem into a Kerning problem. Generally, that latter direction is used for a proof by contradiction, which we use to prove impossibility, and this direction here is used for a direct proof, which we use to prove possibility. The converses there don't really work, and you could think about why that is the case if you like. Now, what separates these two problems, the anagraph and Kerning problems, is whether we're allowed to rearrange the letters in the word. If you're really astute, and by some miracle I managed to actually explain linear logic in that whirlwind, you might have noticed the following. I allow rearranging my hypotheses at will in linear logic, but I could make up another logic where I didn't allow this, where everything has to happen in place. This family of logics exists, and it's called ordered logic. And using the encoding I just did, but in ordered logic, would correspond to the Kerning problem rather than the anagraph problem. Since we know the Kerning problem is undecidable, this would give us a path to proving that the multiplicative exponential ordered linear logic problem, or MEAL, is undecidable using our result about the generalized Kerning problem. I believe that this is true, and also that people already know that this is true. But it is a nice way of tying these three problems together. Okay, we did it. That episode of Tom Academy took way longer to produce than I was expecting, and the resulting video came out much longer than I was expecting. I guess that's the way these things go when you're serious. If you're one of the 3 people in the world that managed to make it through the whole thing and you actually liked it, please let me know. I probably won't do this kind of thing again, but in truth, I kind of miss teaching things that make sense rather than simply making up sort of joke work. So if there are topics that people are interested in, I guess I would be open to the possibility. Okay, thanks. Back to your regularly scheduled YouTubes.